When I see problems like this, I immediately notice there's exponents. These are polynomial equations. So we want standard form and factoring as the strategy. So I look at this, and there's an even number of terms on the left side of the equal sign. It's already in standard form because 0 is all by itself. Since there's an even number of terms, I don't have to do any diamond problem, any splitting. I'm going to start with the greatest common factor of the pair of terms here. So the greatest number of common z's that's in number 1, that's in both of those terms, is z to the power of 5. They both have at least 5 z's. So I'm going to take out my z to the power of 5. And if I divide z to the power of 7 by z to the power of 5, I'm going to show you what that looks like. I put the line through my z's to make it not easily confused with a 2. All right, every time I have z over z, it equals 1. So I have 1 times 1 times 1 times 1 times 1 times z. That's z squared. That's where I'm getting when I say divide by z to the power of 5. I just want to make sure you guys know this and can follow along. When I divide minus 4z to the power of 5 by z to the power of 5, I just get minus 4. And this equals 0. So I have here 2 factors that multiply together to be 0. So I'm going to solve for what makes each factor equal to 0 all by itself. If z to the power of 5 is 0, the only number I can multiply by itself 5 times in a row and equal 0 is 0. Stop moving, little iPad. Come on. So one of my solutions is z equals 0. For the other one, I get the equation z squared minus 4 equals 0. And this is a perfect square equation because I only have a single term that has a square. There's no other z's anywhere else. And I can solve these by square roots. So I'm going to add 4 to both sides, giving me z squared equals 4. And then I'm going to take the plus or minus square root so that on the left side, square cancels square root. Oh no, come back down. So this square root undoes my square, leaving me with just z. And on the right, I get plus or minus square root of 4. The square root of 4 means what number multiplies by itself to equal 4. So that's plus or minus 2. So I have 3 solutions. Z equals 0, negative 2, or positive 2. So what I did was factor out the greatest common factor and then set each factor equal to 0 in order to solve for all the possible solutions. And I do the same thing for number 2. For number 2, I'm going to factor out the greatest common factor. My GCF is equal to n to the power of 4. That's the greatest number of n's that both terms have in common. So I take my n to the power of 4 and I divide it out. And I solve to make each of these equal to 0. So here, when I solve the other factor equals to 0, I set n squared plus 16 equal to 0. It's a perfect square equation, so I can solve with square roots. So I subtract 16 from both sides, and I go to take the square root to isolate n. And what you see is that I get plus or minus square root of negative 16. This solution is not a real solution. In Module 8, we will handle complex numbers and we'll start to take all solutions, not just real solutions. However, in Module 1, if you have you can't take the square root of a negative number. It does not exist. There's no real solution. So the only solution is n equals 0.